1.1, 1.2 solar masses. Otherwise, you get a carbon explosion, carbon detonation, and that's not fit. So, in order to get the oxygen neon core, it has to be more massive. When we look at the X-ray properties of like Nova Del, it's probably going to turn out to be a massive CO white dwarf. There was a Nova LMC 1991 that was about 5 times Super Eddington. We know the distance, and that was a CO white dwarf, and it was that Super Eddington for more than 2 weeks, so that let the theorists think about that. So there's a lot of problems.
There is one planetary nebula that has more neon than oxygen, BOBN1, but that is actually quite a low mass object. And that is pretty much again the intershell abundances brought to the surface and a very low atonicity object.
Neon over oxygen being bigger than 1.
Yeah,
we see that in some of the Nova ejecta also.
Yeah, but in that particular case it's a very low mass object that shows that.
Low mass shell. What about the white dwarf? What about the underlying?
It's probably the 0.55 solid mass canonical. It's not a neon oxygen central star.
There must be another star there.
No, I think we understand why the neon comes from in that particular case. In a very natural pulse, if you got rid of all the helium and you condense all the carbon out, maybe you can get those kind of neon.
I've gone around with the data for this stuff to absolutely everybody, from the theorists to go do the nuclear synthesis. If you look at the mass fractions of all the elements you can get, there is no way, I've sat with Falk for so long, there's no way you can get this 30% neon by mass. There's just no way. And the C2O very low again, the low one, right?
The C over O is very possible in that thing. The carbon is missing.
Yeah.
So can we get the stars close enough in the common envelope phase to get your merges, get your Arco stars?
First one?
I think yes.
First no.
Yes.
Well, I think you get
Yes.
close enough.
I think no one needs the microphone.
Yes. Yeah, I think it's natural. Belgium. It might be the companion of the helium white dwarf. Then you can get the merge, if it's helium 0.2, 0.3 solar mass, then it can merge to all the way in, even if the primary is the lowest. So you can have them in the package. Use basic, especially if you have a center for it. I think.
For the merger scenario to work, while you sometimes see a large shell, it would have to happen during or immediately after the PN phase, so very shortly after the common envelope phase, isn't that correct?
We have 2 white dwarfs that have pretty different masses, so they would evolve at different times in the white dwarfs. So would they have 2 common envelope phases?
No, the first one, it's starting with star more mass involving the RGB, transferring mass to the companion, basically ending the helium white dwarf or something. And then they're close enough so that the helium white dwarf that is left will be engulfed by now the primary, initially the secondary, and they will merge with its core, with its CO. So, well, we need to work out exactly, yes, but I think merger can explain different objects. If you go to 2, you have type 1a. You see some type A supernova happening with hydrogen shell. So they were planetary nebulae. Of course, supernova type 1a are observed very far away statistically. So we don't expect to see at these distances planetary nebulae. But we have type 1a supernova inside planetary nebulae. Merging is quite fast.
Well, we need a nearby 1A.
Well, not too near, yes, but in our galaxy we have.
If you can sketch the nearby one, let us know.
Okay.
We'll be waiting. Professor? Yeah.
I wanted to ask this question to continue the discussion between Solar and Summer. Something came in between, but anyway, still related. So, talking about Nove, I'd like to bring up the object CRL 618, which was discussed in the earlier talks. And in connection with Nove, because as I mentioned, tried to mention, it has these weird isotope ratios. So, it's a carbon-rich star. It has a very low 12 carbon and 13 carbon ratio in the central dense molecular core. And it has a very low 14 nitrogen to 15 nitrogen ratio of a few hundred. It's quite unexpected, and I don't think we could explain it with normal nucleosynthesis of AGB. And we said maybe there's some kind of, and that kind of low nitrogen ratios that you observe in Nove, correct? 14 nitrogen to 15 nitrogen?
We predict that in a typical nova explosion, there should be more nitrogen 15 than nitrogen 14 ejected.
Right, but can you give me an idea of the ratio, of the isotope ratio? Is it a few hundred or something?
Oh no. It's 10.
It's 10, okay. So typically for these evolved stars, the typical ratio for 14 nitrogen, 15 nitrogen is 1,000 or more. So is it possible, but in this object, in the central region, we are observing a 14 nitrogen, 15 nitrogen ratio of a couple of hundred. So we were saying, well, how do we produce this data? And the only thing where we could think of enhanced 14 nitrogen, 15 nitrogen ratios would know it. So I'm just trying to say that maybe there's a connection between an object like this and, you know, and maybe the weird isotope ratios have some connection. I don't know why.
How about offline? Would you give me some references and I'll really check my data and get back to you?
Sure.
I have a question to all, maybe. There's a lot of talk about mergers, two white dwarfs merging. Anyone can picture that event? I have kind of a crazy idea about what happens in that case. I mean, it sounds like it's just like nothing, they just merge, nothing happens. But my picture in my mind is that two white dwarfs touching, something really crazy happens that we shouldn't see. Can anyone explain what happened to white dwarfs merge?
Well, there have been a number of studies, multi-dimensional studies, and we've done some from ASU. Evan Scanapiaco is the faculty member and his students. And I can write out his name for you and just look them up. And they're competing people where they actually have mergers. We're obviously trying to make 1As that way. Violent mergers, not quiet mergers.
So we're doing it at LSU as well, and as the two stars get close together, the helium white dwarf gets disrupted, and the CO white dwarf sort of forms the core of the new star. The helium from the helium white dwarf forms the envelope of the new star.
So it's just a smooth event, disrupting slowly, exploding.
Well, it's very high. I mean, in clock time, the merger is only taking a few minutes.
Start time.
Well, that's what I mean. It's just
Because I've done it, I've taken my hydrocode and treated helium onto carbon oxygen white dwarfs at high rates, and I get violent explosions. Trying to model V445 velocity.
So here the prediction is for violent explosions from the helium accretion. Yes?
Well, we certainly want it to be hot because we want this nucleosynthesis. We want to make selection 18. But it is pretty violent. And the main problem we're having right now is that the helium hitting the CO white dwarf is actually dredging up a large amount of oxygen 16, which is sort of swamping the oxygen 18 that we're making.
Well, the basic physics is that when an object comes close to a compact object, the more the density of the secondary is lower than the density of the primary, within the orbital separation, it will be tidally disrupted. So white dwarf, the lighter one is also the larger one, so has a lower density. This white dwarf will be tidally distorted. This is basic physics. So the question how they come close, by gravitational wave or eccentric orbit, but basically we form kind of material around the equator of the primary star. This is what the people of type 1a do to try to explode type 1a in the double degenerate scenario. And they're so successful that are different models, so actually they don't know. But this is the basic. So if it's a helium white dwarf, even if you ignite the helium, it's not explosive, you form a composter, because you ignite the helium on top of the CO white dwarf and the rest of the helium expand. You have 2 CO, it is very complicated. It's not clear if you have ignition when they merge or you not have ignition. If you don't have ignition, the disrupted CO white dwarf might form, according to one calculation, huge, giant AGB star with CO envelope. So it is not so clear. Also, to calculate the energies as liberated is very complicated. The moment you start to become close to each other, second masses, well, it is complicated because you come to the range of relativistic degenerate electrons. So this is a very hot topic in the type 1a community. But
is it minutes or seconds?
The calculation or the merger? The calculation takes career of people.
But you will get a thermonuclear runway, right?
Yes.
Well, sometimes yes, sometimes no, depends who you ask. There is no good model for type 1a super. We don't know that. There is no agreement on the scenario. Even people who agree on double degenerate or two white dwarf merge don't agree when it is, when the explosion will occur. Immediately, violent mergers immediately or will wait. So, it's a good question.
Bruce?
This is a change of subject. Andre, talking about search for planets around giant stars. You pointed out the discovery of planets close to the stars such that they would be engulfed on the AGB. Can you say anything about ones that are further away, or can you set any limits? Maybe the ones that already have a planet, it's hard to detect the second one, but how about the other half that you didn't find planets? What can you say about ones further out that won't be engulfed?
Well, it has been calculated. It has been calculated a number of times. The zone of the engulfment around stars of different size. It actually is connected with the tidal force and the final radius at the helium flash. So in the case of the stars that I pointed out, they were about 1 to 2 solar masses. So I would say that the zone of engulfment would be around 1, a bit more astronomical units. So all the planets that I showed were exactly within the zone.
But could you, the fact that you didn't find ones further out, does that tell us something? Because you should be sensitive to them, correct?
Well, it's a question of time, mainly, because you need much more time to find long period components in those systems. But we would see them already, because we observed the stars already for a number of years. So even if not full orbits, we would see at least a trend in radial velocities, which is not the case, at least in the stars that I studied.
Because it looked like you've been doing it for 8 years.
Yes,
To
something
find
like that.
just 1 year periods.
Yes, so we can reach up to a couple of astronomical units already. And indeed we have systems where long periods of components exist, but not yet in those ones.
Can I say we have 2 minutes? I would like to, what I take from this entire session, not specifically on an object or type of object. I think what I take is that we are dealing here with several very non-linear processes. I'll give example of 2. One is binary interaction in a non-violent way, this tidal interaction. Tidal interaction extremely sensitive to the ratio of the AGB radius to the orbital separation. So if the AGB expands eventually start to interact tidally with the companion, tidal interaction, and it will happen very rapidly because it depends, depending if you look on synchronization or circularization, it depends on the ratio of radii to the power of 6 or 8. So it is very sensitive. So for a long time we see almost no interaction, we see spherical AGB, and then the moment the tidal starts and it accelerates itself. This is one effect as an example. The second one, and I can relate it to all people who presented here AGB star with model of rotation, it might be just tidal locking to a companion, even no tidal locking, just tidal bunch without synchronization. And another nonlinear effect of binary interaction of planets. If you take 10 Jupiter mass planet, it will not do much, it will not interact tidally strong, but eventually it will enter the envelope, and then when coming very close to the core, to the point it survives, several solar radii, which is deep in the envelope, then it releases huge amount of gravitational energy, can excite waves and so on. So another binary non-linear effect. The second one is mass loss, and our both show it clearly. You form dust on 7,000 degree Kelvin star, and here we have a non-linear effect coming from shocks. You have pulsation, you excite shock, you first heat the gas by the shock, but then it cools radiatively, and then it cools adiabatically by the expansion, and then you go to temperature of 2,000 degree Kelvin, and you form dust. This is a highly non-linear effect. And these highly non-linear effects, I gave example of binary interaction and mass loss from dust, but I assume there are more, I think, common to most of the talks today. They are non-linear, so as I said before in this meeting, we are not looking for standard candles here, forever candle, I don't know, but standard planetary nebulae. In the past I had a paper why every bipolar planetary nebula is unique. Because almost every planetary nebula is unique in the sense what is going on. And I think some of the nonlinear effect we can see even in the talk on this post-RGB nebula, which evolves very rapidly, very clearly a nonlinear effect going also with the helioflash that turns into an SDO star, which is a nice scenario because we see SDO come in general from binary interaction. So it's a general comment. If people can add to that, it will be very important because in the past we were looking for standard planetary nebula. There is no such thing as standard planetary nebula.
Anyone would like to comment?
Was that a question?
So say. I agree with no. And he is fake.
Is anyone agreeing with no? Any more questions?
Rudy has something he should show. I keep pestering him to do it. As long as Sumner is up there. Okay, can we on the projector? Can we turn on the projector?
Yep. It's coming.
We'll have to shine the light right on Sumner.
I'm not very reflective. Ambiguous.
Yep, you're coming.
Yeah, okay. So, this is a work that I did, or I'm working on still actually, but... Oh yes.
Who has the microphone?
I do. So this is work on the recurring nova RSO, and we stopped it for it. You can see the big reveal. This is a recurring nova that was mentioned earlier. It's in a pretty wide binary, like 400 years, and
No, 400.
400 days. Yeah, 400 days, and
It went outburst in 2006, and we got these Chandra observations of it in 2009. And you see this, you see this extended emission out here. And then we got another observation. Oh, sorry, this is the unprocessed image, this is the reconstructed image. And then we got another observation in 2011, and you see this ejecta has actually expanded. So we went back and looked at all the radio observations that you saw earlier, and we put them all together. And these are the radio. This is HST, these 2 points here, and these are our 2 X-ray data points. And all this material in the east-west, although you have to take it with the caveat that we don't know necessarily that the emission processes from each of those wave bands are measuring the same material, but there seems to be some east-west material that's freely expanding, and it seems bipolar, which is the thing that we can't understand now, and the thing that the theorists can also probably help us with, is that there is a disk around the white dwarf in RSOs, and we don't know if that disk is responsible for shaping this material, or if it's the circumstellar material that Shazarine has modeled very nicely. And it's just the expanding glass wave